All right, good afternoon. All right, so we are picking back up with metals, complexation, all that stuff. I've got a few takeaways, just kind of recap what we talked about last time. Make sure we kind of see what are kind of the important spots, or what I was reflecting on, feeling like, hey, these are the important concepts that we talked about. One is, what is a ligand, right? What are we actually talking about when you hear that word? It's something that's a molecule that's attaching to a metal, and giving that metal a better environment to hang out in water, basically solubilizing it in some sense. Even water can act that way. Maybe we call water a ligand, or maybe we just say water complexes it, and then a ligand comes along and we call it something special because it's more favorable than water. Doesn't really matter too much, but the idea is that a ligand is something that's complexing with metals to give them a better interaction with water as a whole. We also talked about chelates, which would be a ligand. It's a subset of ligands that have multiple attachment spots. So chelating is kind of like a claw. So it's a molecule that's acting like a claw and grabbing a metal, and therefore it has kind of more strength. So if you have one little finger that has some sticky tape on it, you can grab that metal and it has a little bit of cohesion. But then if you have 5 of them and you grab, you're holding on tighter, right? So chelating, we have some increase in the bonding strength for that. And in general, we can think of when and why is binding strength important. If we take a look at, maybe we're trying to figure out toxicity or solubility or something like that, what kind of a ligand is going to make an impact in our system? There's a few ways we can look at the strength and a few factors that would affect it. Inner shell versus outer shell, where you've got water first, or the ligand directly interacting with the metal. A number of attachment sites. So if you have a 2-pronged chelate, you can grip a little bit, but maybe 5 is better. But if you try to put 10 on there, maybe you have some awkwardness, right? And it starts getting a little weaker the more you add, after about 5 or 6. You wouldn't want a hand with 10 digits, I think. It would make grabbing a ball pretty awkward. Your hand would have to be shaped pretty funny, right? It doesn't seem like it would work too well. Okay, then the electronegativity of the metal and the ligand can be important, and the size of the metal ion can also be important. And some of that has to do with charge. We didn't really go into it, but polarizing the metal, pushing charges around a little bit, how it's all shared, but just letting you know that those two things can be important. And then we took a look how we could calculate a whole bunch of equilibrium constants and equilibrium values so that we could understand, if we have water plus some other ligand, how do we know how much of this metal is in the form of the ligand? We used zinc as an example. Zinc with hydroxys versus just zinc with waters versus zinc with ammonia, I think is what we were using. So depending on what we've got in there, there can be many forms of this metal as a dissolved species, and we saw it can get pretty complicated, but it's possible to calculate that. So we'll revisit that just a bit today. Okay, so those are kind of the big ticket items. I wanted to kind of start there, remind us what that's about. And today we're going to point towards solubility as something that we're really interested in. And solubility really brings us back to kind of the basics of equilibrium. So we're going to kind of revisit that a bit. And ultimately, we will be able to see how we can graphically approach some of this. So tying in a little bit of that second section of our class so far, having it in mind, oh, what if we titrate something? Or, oh, what if we plot this out to figure out where is it soluble, where is it not? Some of the same tools and same ways of thinking is kind of where we're going. So to solve a complexing situation, a complexation problem, we could use algebra, and we could do a manual graphical approach, but really that's not very practical. So I'm going to show you today a couple of snippets of a program that does this stuff. Mentioned it before, only going to mention it today, kind of point you to some resources if you need it. But because we're doing MATLAB and Excel, I'm not going to go into this program for us more than that. But it is a common one. It's in all the textbooks, and it's been around for a while. So we'll get to that. And then, as we'll see, and as we kind of hinted at last time, acid-base reactions can also impact our solubility, of course, and it has a lot to do with, are we adding that OH to the metal, or is it just water, right? And if we get the OHs, that could cancel out some charges. We could get a non-charged species, which tends to be happier to precipitate out. So we'll see some hydroxides and things like that. Okay, well, let's take a look at a very simple case, I'm putting the very simple in some air quotes here, of metal chloride in seawater. This is an example the book takes us through. We're going to breeze through it, but also kind of read what it's, at least the big picture of what it's talking about, and see what would it take to understand or characterize lead in seawater. We actually talked a little bit about gold in seawater last time, but this time we're gonna go through this as how much lead is there. So we can assume for this example problem that we have really no impact on the amount of chloride, because lead is a trace metal. We have tons of chloride in seawater, as we'll see, and a tiny bit of lead. So even though we're complexing, we're taking away some chloride, meaning it means nothing compared to how much is there. Okay, so that's one assumption. Another assumption is we're going to say, at least at the start, no complexation by DOM or organic ligands. Okay, so I'm going to ignore some other possibilities there. So it's lead with chloride, and I guess possibly some other non-organic, so inorganic species. So here's the example. And this is our primary book, so you can take a look if you'd like. So abundance of monochloro lead to complex in seawater. So lead exists in natural waters primarily as lead 2+, or that's kind of in the +2 oxidation state. Its total concentration in surface layers of the world's ocean is something like 14 nanograms per kilogram, which is nanograms per liter. Or we could write that as 7 × 10 to the -11th moles per liter. Now, Liam is a new grad student, is limited chemistry background. So think of yourselves, by the end of this class, you have pretty good chemistry background, but we're halfway through the course and you're not feeling great about it. So you might feel like, okay, I've got limited chemistry background. Maybe I'm not ready for this. So think as if you're him, okay? Is told by his advisor to calculate lead speciation in seawater, and he's also told that that's dominated by chloride because the concentration of Cl- in seawater is so high, more than half a mole per liter. So Liam proceeds to calculate the fraction of Pb2 complex with chloride in seawater, and initially finds a stability constant for the monochloro lead complex. So this is lead 2+ plus Cl- is in equilibrium with PbCl-, a little hard to see, or excuse me, PbCl+ because it's 2+ and 1-. And we've got a equilibrium constant for that. Log K is 1.56. Great. So erroneously thinking that these are the only species that need to be considered, he calculated the distribution of lead between lead 2+ and lead Cl+ as follows. So far, that's something that you probably could have done, right? It's like, okay, I've got an equilibrium constant, I've got the concentration of chloride, and I've got a total lead concentration. Okay, I could figure out how much is in which place, right? You've done problems like this already. So first he let's see, let me go back up. Okay, he calculated the distribution of lead between 2+ and the PbCl+. So first he corrected the stability constant for concentration based, so he computed the activity coefficient. He did that part. You've done that part, you could do that part. Use the Davies equation, we talked about that. Ionic strength of the seawater, got a value for that. Found the activity coefficient for monovalent ions and a different one for divalent ions. Put those in, and he got a corrected K value. Okay, we didn't talk too much about the correction, the K value, but you could do it. It's not that crazy. I'm not asking you to do it, I'm just saying. You've seen enough of the ionic strength stuff, you could do that. So he's got a K value, great. Then he uses that and puts that in at the bottom here to find a concentration for PbCl plus would be 4.59 times the concentration of Pb2 plus. With that, he now knows the speciation because you add up that plus Pb2 plus by itself and you should get some value as the total. So he wrote out the mass balance expression, say the total is known, that's going to be equal to the 2 plus this PbCl plus, and he could solve. Okay, so he solves those, great. Now he showed that to his advisor, and Liam learned that Pb2 can form more than one complex with chloride, and was told to do more research into stability constants for these complexes. Undaunted, he readily found a tabulation. So he went and found a table, stability constants with a reference book, and learned that you've got 4 complexes. You get PbCl plus, PbCl2 with no charge, PbCl3 with a minus, PbCl4 with 2 minus. Okay, so we've got all those constants, great. And then it carries on, he does some more math, basically continues that process and kind of does what we talked about last time. All right, so he eventually finds that about 48% of the lead total exists in the monochloro complex. So the place he started, he was pretty close, but that was only about half of the lead, the total lead is accounted for with that one that he calculated. So I say pretty close, but he was 50% off, right? So in a way, kind of close. At least a good start. Okay, as a check on his calculations, he added the concentrations of all 4 complexes together to make sure that went to the total. That was good. So he took this to his advisor again, and then he heard his advisor was like, well, nice try. Better than the first one, but didn't you realize lead forms complexes with other major anions in seawater? He's like, so try again. Still undismayed, so wow, he's a honey badger. So although perhaps a bit weak in chemistry, not lacking in self-confidence, Liam decided to look at the thermodynamic database in this vMinTech thing. We'll talk about that in a minute. That's the program. So I like the way they say this. It almost feels like, oh, he went and cheated. Went and looked up the answer online. No. But actually, when you get to this level of that much chemistry, that's the right way to do it, right? It's kind of like doing a long division problem. Yeah, sure, you could do it by hand with X number of digits, but probably get your calculator at some point, right? Okay, so he went there, found constants, and found that there was complexes with not only Cl minus, but also bromide, sulfate, bicarbonate, carbonate, and fluoride. Okay, so now he's got a lot to deal with. So clearly it makes a lot of sense to then use a program. So the book continues to describe some of that process. Didn't find it too interesting. And then he creates this table and notices that from this table we'll look at in a second that not all 19 of these complexes are super important. Some of them really don't have much concentration. And so in some sense, I guess you could probably, if you're doing this manually, you'd have to find which ones you can kind of ignore. Okay. But overall, we can see how time-consuming that could be and why you might need some program in this very simple case, okay, with just what we thought was lead and chloride and seawater. So here's the table, and we can see all of these different complexes. We've got the chloride, the fluoride, bicarbonate, and bromide, and sulfate, all these pieces. And one thing that's kind of interesting to note is one thing they did is they were taking this log beta value, that was kind of that cumulative thing that they were talking about, and summing it up to see what the total was. And if you remember, we had written this out last time. If we're using lead, we said something like, let me say the lead total was equal to the lead 2+ times 1 plus some fraction for each. Like we have, if we're counting the total lead, we want to count the lead 2+ plus the lead chloride, plus the lead dichloride or whatever, plus the lead fluoride, plus each of these species, right? And we put it in terms of these, different betas and K values, right? So the beta probably over some proton plus blah, 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 blah. Okay, so they just added all these up to say the sum here within all of this, I think, is what they're calculating here. So it might be a handy way to do it, to get the log of that and to say, all right, well, the total fraction here has some value. So anyway, just kind of relating that you could get some summation and find information like the ligand concentrations here, how much was bound to chloride, fluoride, and blah, blah, blah. Okay, anyway, I just wanted to show you this can get quite complicated, and we really need some calculator type of help if we go that far. And that's where this software, it's free to download. There are instructions online. So if you ever do get to the point where you have a challenge with a chemistry system like this, perhaps with senior design or something like that, you might think to yourself, oh, there's a program for this. Maybe you're taking a look at your homework and you want something to double check. Am I on a good route with this? What else could I do with this? Maybe try it out and you just see like, hey, what can this do for me for this problem? So it's a bit old, so I think you shouldn't expect something super fancy graphically or anything like that. But it has great built-in databases of all these constants. Okay, so there's a lot that has gone into this from the kind of aquatic chemistry. I think more than that too. You can see there's also some gases. We'll talk about redox soon. Lots of different possibilities here, all relevant to kind of the world of geochemistry and aquatic chemistry, especially with equilibrium stuff. So check that out if you like. There are lessons online, beginner lesson linked here, link to download it. This is VMinTech. I think it's Visual MinTech, and forgetting what the MinTech stands for, but there you have it. Okay, so a couple other things, as we look at such a large amount of equilibria to deal with, I wanted to highlight just real quick, as we start thinking about the relevance to solubility, hydroxy complexes are an important one. So last time we mentioned these, and I wanted to kind of come back a little bit, we can replace a water with an OH minus. Or, and I was talking with Mason about this at the start of class, we could also look at it as if the water that's already attached is going to be in that equilibrium reaction where it could lose a proton. So either way you look at it, there's an equilibrium going on there that involves water potentially losing a proton and the water that's attached to some metal. So if we have a hydrated metal and then it starts kicking off some electrons, or excuse me, some protons, then we will end up getting these metal hydroxides. And if you look at it, each time you're doing that, you are kicking a proton off into solution. So if you take a bunch of ore from deep in the ground where you have metals and they reach the surface and now they're oxidized, and you're, let's say, rinsing your mine tailings to kind of get the dirt away, to separate dirt from your ores. Pretty natural, common thing to do. One thing you'll notice is as water's attaching, there's going to be protons leaving, which means you're adding protons to solution, which means you now have what we call acid mine drainage, because that hydrating of the metals is releasing a bunch of protons. So just that simple interaction of oxidized, so some metal that is in a plus something form, reacting with water and then giving off protons will ultimately get you that acidic condition. Yeah.
So is that like essentially like a mine? I'm assuming you're mining metal, right? And then if it's exposed to moisture, then it's gonna complex with that and then create an acid like mine drainage.
Yeah. Okay. Yeah. Now it also has to be in an oxidized form. So sometimes when you extract it, you might get metals that are zero valent. That would be kind of your salt. Like probably usually not, but if you did like have a an ore vein that was like, you think of like a pure metal, then it's not much of that's oxidizing. But generally that's not how it's going to work. Generally you just have a high fraction of iron or aluminum in that, and later you're going to reduce that probably with a lot of heat and all that, and take it from an oxidized state to a reduced state. So normally you're drawing up ore that is already at least somewhat oxidized. But even if it wasn't, maybe the oxygen in the environment speeds that along, and then you have the acid mine drainage. So there's a couple things to note here. One is the H plus leaving will give you that acid mine drainage effect. And the other thing is that we have a lot of hydroxides, metal hydroxides, that will precipitate, in part because the charge reaches zero. I think there's some hydroxides that are still stable in water, but you're never going to have something precipitating with a charge, right? You don't have solids that chemically have a charge there. You might have a solid that ends up with a net surface charge, but the molecules forming the structure itself are not charged. So partly it's the charge destabilization. So you could think of aluminum that's normally in a 3+, now has 3 minuses there. Iron can be in the ferric 3+, or ferrous 2+ forms. Zinc is a 2+, and magnesium is a 2+. So as we see, some of these hydroxides are fitting in that they're satisfying that charge. At certain pHs, they're likely to form. So you can see how if the pH is kind of dictating in part whether or not that H plus is leaving, or whether or not there's enough OH minus there around to add to it, that will kind of tell you whether or not you get the solubility, right? So a couple things there to consider. Now, one of the most common, or perhaps popularly used solubility manipulations when it comes to like ligands and chelating agents is something called EDTA. If you want to be fancy, you could call it ethylene diamine tetraacetic acid. Acetic acid that's vinegar. And so tetraacetic acid means we've got 4 vinegar groups. And so if we look at this molecule, each one of these is sort of what we might call acetic acid. And the ethylene is this portion, and the diamine would be the 2 amine groups here. So big fancy word, we usually call it EDTA. And the deal is we can treat this like a multiprotic acid. If you look at each one of these OHs over here, they could lose that H plus, or lose the proton to get a minus. And so we talked a lot about HA, right? And then eventually sometimes we talked about B2, HA and H2B, right? As a monoprotic acid and a diprotic acid. Well, here we have H4Y, okay? So we can have quite a few protons leaving here, and in fact, It could actually even accept a couple extra. So we could even get a positive charge. So we have a lot of equilibria with just this molecule. But the interesting thing about it really is that it acts as a very nice chelating agent, the claw type of thing. If you look at it, and if you are familiar, if you remember from your survey of organic chemistry, when we've got these bonds here that are not saturated, so we don't have any double bonds between these, here, any of these, those are all going to be a little extra flexible. When you get double bonds, or especially triple bonds, you're getting rigid. You're getting kind of stuck in that direction. But the carbon bonds like this that are not, they tend to be a little more loose. So this is a little bit like a starfish with long tentacles. And it's going to wrap around anything that has a coordination number of 6. And the coordination number of 6 comes from the fact that we've got 2 nitrogens, and then I believe 4 of the oxygens, probably these guys, and maybe I have this written somewhere. All 6 of those spots can act as a little grabbing spot to chelate a metal. So it works really well with divalent cations that have a coordination number of 6. Just happens to be very, very strong complexer for those, calcium and magnesium in particular. And you've probably heard of calcium and magnesium whenever you've heard anybody talking about the hardness of water, the mineral content. They're not necessarily hazardous to drink or to be in your water, but they can be a pain because they'll cause precipitation. They are essentially what we call hardness. And so we use EDTA to measure hardness because we can use it in a particular manner where we can essentially take, if we add enough EDTA, we've complexed it so that it can no longer act like it normally does. So if we thought about just calcium for a moment, if we wrap every single calcium with one of these little EDTA molecules, we've grabbed it, and now calcium's not going to precipitate like it normally would if we give it conditions where it would precipitate. So we can use this for a lot of things. One is to measure hardness. Another would be to prevent scaling. For example, if you don't want it to precipitate, maybe we add a bit of this stuff and it kind of stabilizes it. So there are some interesting things, in particular the Y4 minus. So when we lose all the protons, a very basic condition, that one tends to be the strongest grabber. Y3 minus, HY3 minus also does a decent job, and the next one over does a little bit of grabbing, but mostly it's the Y4 minus. So we could look at the K value. So log K here is about 11 for the point where we have the equilibrium between, this is going to be the HY3 minus in equilibrium with H plus and Y4 minus. Right, so when we talk about these showing up and we'll look at a plot, you'll see it looks a lot like what we've done in the past with acid-base reactions. It's just that there's several reactions, so that it's a little more complicated. But the thing is, we are interested in this one that happens to be quite a basic value. So bringing that forward, I just said this last pKa, or this last Ka value, was right around pH 11 because it was 10.9 or something. Here we see it showing up where we have equilibrium between Y4 minus and HY3 minus. Those cross right around just under pH 11. Okay, so you've seen this stuff before. We've talked about acid-base. So this EDTA stuff is going to act kind of like an acid-base system. And it's going to work effectively when we have a lot of Y4 minus. And possibly it'll work still when we have HY3 minus. Yeah?
Does the Y represent the complexation molecule?
Yeah. So here Y is EDTA. Let's do that. Now, in this case, H for Y is formally EDTA when it's at its zero charged, fully protonated state. So Y by itself would be essentially what we get if we took this molecule and dropped all the protons. But yeah, you get the picture. Just like HA and A minus, right? So A could stand for acetic acid or hydrofluoric acid or whatever. But when it's just A minus, that's the deprotonated form. Okay. So there's a bit of a question here. We might ask ourselves, if this is the strong stuff, and this kind of works, and maybe this works a tiny bit, well, what pHs is this really going to function for us if we want to use it to stabilize calcium or magnesium or something? So that's part of, that is a question we could ask. And I've got a video that will show us how this is used in practice. We can actually titrate a system with EDTA. We talked previously about titrating with a base or an acid, but in this case we can titrate with EDTA to watch at what point does calcium 2+ just complexed with water disappear. Because if we add enough EDTA at the right pH, it will all grab up the calcium and kick off all the waters. So we can find that moment if we do a titration. So I'm going to show you a little bit about that. So this example in the book here is describing, well, how do we know at what pH is that going to work? The answer, the practical answer, I think, is generally pH 10 or above is typical. You might be able to go down a little bit, and we're going to take a look at a graph here to give kind of some examples. So if we did this at pH 5, what we're looking at is a titration plot where we're adding EDTA on the x-axis. The y-axis, what we're looking at is calcium that is complexed with water. So it's just Ca2+. Nothing particularly interesting about it. So when we drop that to a very, very small number, that's when we're seeing, oh, okay, the calcium has all been grabbed up. If we use a very low pH, it's not working very well. It would be pretty hard to see that change when titrating. We add a little bit of stuff, and we see a tiny, tiny decrease in our calcium. We're not even sure if we really measured it correctly, right? We keep adding, we keep adding. We don't know where the spot is where we've added exactly the right amount. What we want with the titration is when we add exactly the right amount, then we go boom, big drop, okay? So then there's a bit of a question. We see, okay, well, pH 7 looks like it works pretty well, but there's still a bit of a question about, is that a big enough drop? And so the book goes on to describe that. We really see pH 10, okay, yeah, we really made a big difference there. That is clearly a good enough drop. So this one, I'll say, is a bit of a question, and this one's working great. Okay, so I want to show you this YouTube video. So just give me a moment.
The determination of water hardness. Attention, in this experiment, the determination of water hardness. Attention, in this experiment, hazardous
Okay. See if I get the sound. Just give me 1 second to get the sound through the thing in here. There we go. Okay, so all credit to the people who made this video, just kind of using it here to share with you guys in class. Oh, wrong one. So this will be a titration with that EDTA. You'll also see that there is a another indicator molecule that's added. Essentially, the indicator molecule, when there's calcium around, it changes color. So what's going to happen is the EDTA will steal the calcium from that indicator molecule, and then suddenly the indicator molecule will be like, I know I don't have calcium anymore. I think it changes when it has calcium. I think it's kind of a reddish, maybe pink. And then when it loses the calcium and it's just sitting there with no calcium, I think it's blue. Okay, so we'll see the color change instantly that way. There's also another way you could change the pH and precipitate calcium to measure whether or not it's there that way also. But
Compounds are used. I don't take any experiment to run for a short while. When it has been sitting in the pipe, it is possible for it to contain additional contaminations like heavy metal ions, which can have an influence on the measurement. 3 solutions are needed. A buffer solution with a pH of 11, which is an aqueous solution of ammonia and ammonium chloride, an aqueous solution of sodium EDTA, and a solution of areochrome black tea in ethanol.
that's the indicator.
For the titration, an Erlenmeyer flask with a stir bar is placed on a magnetic stirrer. Over the flask, a burette is placed. Before filling the burette, it has to be made sure that the stop cork is closed. Then it can be filled with the EDTA solution. At first, bubbles of air are trapped inside, which is why the burette is filled above the highest marking. To remove them, the stop cork is opened somewhat quickly and the excess solution is collected. Then the level of the solution can be adjusted to the highest marking. The meniscus causes the broad line on the back to taper, making it possible to read the values precisely.
So he's just setting it up so that you can really measure the change in amount of stuff he's adding, right? Just getting everything all set for that.
Next, a sample of 50 milliliters is taken from the water that should be measured. Then the indicator is added. It was found out that the amount was way too low, so more should be added. After adding 10 milliliters of the buffer solution, the sample is ready for the titration. In the first run, the EDTA solution can be added quite fast, then the following samples can be determined precisely. The solution changes its color to blue when the titration is finished. To the end, it is important to wait a few seconds between the additions because the change can take a while. It can take several seconds until the color change takes place.
So you just saw it change there.
In the first run, 2.6 milliliters of solution were added. In total, 6 samples were measured and at the end the mean value was calculated. Then, per milliliter of EDTA solution, you get 5.6 degrees German hardness, which leads to a value of 14.45 degrees German hardness. This is quite high, but close to the value of the water utility. Due to the distance to the water source, it is expected that the values tend to vary, as it can be seen here. The unit, degrees German hardness, is only used in Germany and very old, which is why there are a lot of different units for water hardness.
Okay, so that's about it. Since as he was just describing, that's kind of a weird unit. A lot of times you'll see for us, we would say either parts per million or milligrams per liter as calcium carbonate. Tends to be a very convenient one. the molecular weight of calcium carbonate is exactly 100. Simplifies a lot of calculations. It's just really convenient. So that's what you would normally see, and there's a conversion factor there, so we could convert the water if we want. You know, we could figure that out. I think he just goes on to talk a little bit about that. But that's the titration with EDTA, and you get to see that nice little color change. And you can kind of see how he was prepping that. He did a few runs, got first an estimate of how long it was going to take, approximately what volume, and then he narrowed it down, was a little more precise, and took some average there. And then once you know how much EDTA you had to add to cause that big drop, that's just like in our titrations. When you see the outcome change sharply, you've reached the amount, in this case, not of an acid, but the amount of calcium. Or more accurately, in here with the hardness, it's calcium and magnesium. Both of them are acting in the same way in terms of complexing with the indicator and complexing with EDTA. So EDTA really likes to grab it, and this other indicator molecule does grab it, but not as strongly. So EDTA just rips it away, says you're mine now, and then you get the sad blue indicator. That's how it's working.
So whenever the color changes, is that the equivalence point? Or am I still getting that?
So the color changes, you could almost call it an equivalence point, except calcium is not an acid.
Yeah.
But it's a similar concept, right? We look for the acid to reach that equivalence point to say, okay, we've added an equivalent amount of H plus to the system, or OH minus, to get it from the one equivalence point to the next, which is the amount of acid, the total amount of acid that's in there. In this titration case, it's a very similar concept, but we're adding as much EDTA as there is calcium and plus magnesium in the system. So it's a very, very similar concept. We just wouldn't call it an equivalence point because it's not not an acid or base. Okay, so if you're curious about the indicator molecule, you could look it up. That's the molecule there. It's called areochrome black tea, used pretty often for that specific situation. Okay, I wanted to mention one other scenario where we have environmentally important ligands. Cyanide, heard of as probably rat poison and things like that, dangerous stuff. It actually works quite well, and there are some metals. There are entire classifications of what kinds of metals or what kinds of ligands. I'm skipping all that for you guys. I think it's a little not super important, but you can classify metals in terms of what types of complexes they like to make, inner shell, outer shell kind of stuff, things like that. So for one class, cyanide is a really strong ligand for them. So you might actually recognize that sometimes you use cyanide for things like silver or gold, grabbing them. So zinc is one example. So cyanide itself is toxic, but sometimes we end up using it. So just wanted to show you, if we're adding cyanide to a zinc solution, we can see a lot of interactions in terms of what portion of that total zinc is going to be in different complexations with zinc. Would also have different pH effects. So just showing you this, that we can take a look at a lot of different species and speciation, and ultimately select, oh, okay, I want to grab this metal, this something, and stabilize it. So I'm going to use this pH and a particular concentration to make sure I can engineer my system accordingly, right? We can design systems based on these speciation diagrams that we could make. That's kind of the point, yeah.
Is OH minus and cyanide present, like, because, I guess, are they competing with each other for zinc?
Yeah, so good question there. So we're always going to have some OH minus around because water can do that, right? And then if we also have cyanide in it, it's a lot like what we were looking at yesterday with zinc hydroxide and ammonia, where we're just going to have some competing competition for the for the ligands, right? Or between the ligands. So, exactly. So, sometimes we may have some mixture. Okay. So, I want to shift gears a little bit, bring us back to some of the basics of equilibrium and talk about solubility. Now, I think I have mentioned it a few times, but I just want to be a little more precise with it, properly introduce the solubility as equilibrium reactions, cover the fundamentals, and also give a few common rules that we can find on the Libre texts chemistry website. It's kind of an online textbook sort of a resource. So, when we dissolve something, we have an equilibrium between precipitation, making the solid, and dissolution, grabbing that solid and turning it into dissolved stuff. So if we have a swimming pool and you throw in a brick of salt, if it's a big swimming pool, probably that whole thing will dissolve. But if you keep throwing in bricks of salt, eventually you'll have solid salt in there because it reached saturation, right? So once you get to that point, then you have an equilibrium where there's excess solid there that could dissolve, and it probably is dissolving, but you also have precipitation at the same rate, right? We've reached an equilibrium at that surface. Salt is just an easy example. There are all sorts of minerals and things that can dissolve and precipitate. So what we're talking about then is this back and forth reaction. Now, if you have a condition that, let's say, table salt, most of the time if you're adding table salt to something you're cooking, you're never anywhere near the point where it's not going to dissolve, right? You've done something wrong if your salt's not dissolving, if you're cooking. So a lot of times we've treated sodium chloride in particular as an irreversible one-way reaction. There are cases where it will not be, right? We can think about how we actually collect salt in salt flats. We let a bunch of seawater dry. Eventually, enough water leaves that you are starting to form precipitated salts, for example. You can do this anytime you could take salty water, pour it on a pan and dry that pan. You'll have some little salt residue there, right? In fact, if you've ever been out in the Louisiana heat, sweating a bunch, and you have like a t-shirt on and then you let it dry off, you might get like a rim of salt where your sweat was. Maybe you guys don't sweat as much as I do, but it can happen. So you can see in different situations you get precipitation. Okay, so we would say the dissolution reaction for it set up like this would be the reaction heading to the right and the precipitation to the left. So salt may not be the best example. In an inverse, silicates are very insoluble, so they might be a good example of when you almost never dissolve them, or only a tiny, tiny bit of them would dissolve. So something like that where you might get some silica hydroxide. Mostly you're going to have some silica oxide. So quartz is an example that contains at least some form of a silicon oxide, and you can imagine just from your own knowledge, quartz doesn't really dissolve too well. Okay, so here's a few rules. And by the way, even before we get there, maybe this is on the next slide, but for any equilibrium reaction, we can write up the K, and this time I'm going to call it solubility product, KSP. It's the products over the reactants, right? So we're going to have, for example, sodium times chloride divided by sodium chloride. Now, you'll remember perhaps that we treat solids and liquids as one, as unity, because if we have a brick of salt, it's not really changing when we dissolve a little bit. Assuming we still have some solid present, the concentration of that brick hasn't changed. It's still solid that is present. It's probably the best way to look at it. So that means that anytime we're dealing with a solubility product, it's basically the K will be equal to the different species times each other. Okay? Now remember, if we had something like calcium chloride, CaCl2, in equilibrium with 2 chlorides, we'll just say, 2Cl minus plus Ca2 plus. In that case, the 2 there in the chloride has to become an exponent, right? So then K in this case would be Cl minus squared times Ca2 plus. We've seen this before. You know that. I'm just reminding you that. Okay. Okay, so let's take a look through the rules. Some common solubility rules that are good generalizations. Okay, first of all, salts containing group 1 elements. That's like our lithium, sodium, potassium, cesium, and rubidium? What is it? Rubidium. They're generally quite soluble. There are a few exceptions. Salts containing ammonium ion are also typically quite soluble. So the group 1 and ammonium tend to be quite soluble. Salts containing nitrate are often soluble. The nitrate is NO3 minus. Okay, salts containing chloride, bromide, or iodide, so a lot of our halides, are generally soluble. Some important exceptions would be with silver, lead, and mercury. So silver chloride, lead bromide, and mercury chloride are insoluble. And in fact, last time we looked at silver bromide with the photography, right? It was also insoluble. Most silver salts are insoluble. So silver nitrate is an exception to the nitrate thing. And then silver, is that acetate maybe? C2H3O2, common soluble. Salts of silver, virtually all others are insoluble. Sorry, so that was not an exception. So those two are soluble, but almost everything else with silver is insoluble. Okay, there's some more. I'm going to run through these with you, but hopefully you'll be able to start connecting it with maybe something you've seen in the lab, or just like, okay, maybe I've heard of that, maybe I've never heard of that. We'll just go through them real quick. So most sulfate salts are soluble. A few exceptions: calcium sulfate, barium sulfate. So this is gypsum. So you probably heard of that before. That's the main ingredient in our drywall. Lead sulfate, silver sulfate, and strontium sulfate, all exceptions. Most hydroxide salts are only a little bit soluble. So hydroxide salts with group 1 elements like sodium and stuff tend to be soluble. So sodium hydroxide, very soluble, right? That's the base that we use. Where was that? Hydroxide salts. Okay, so let me see. Of group 2 elements, calcium, strontium, barium, are slightly soluble. Hydroxide salts with transition metals like aluminum, we talked about this, tend to be insoluble. So FeOH3, AlOH3, cobalt hydroxides, not soluble. Most sulfides of transition metals are highly insoluble. So cadmium sulfide, iron sulfide, zinc sulfide, silver sulfide, arsenic, antimony, bismuth, lead sulfides, all pretty much insoluble. Carbonates are often insoluble. A few examples there. Chromates, often insoluble. So lead chromate. So chromate being chromium plus 4 oxygens would be chromate. So those as part of the salt. Phosphates, such as calcium phosphate, so CaPO4,2, and silver phosphate, frequently insoluble. Fluorides, frequently insoluble. Okay, so a bunch of rules. I don't need you to memorize all of those, but hopefully you kind of thought at least a few of those, like, oh, okay, that's something like that. I pointed out gypsum, right? A few of these I hope you're kind of connecting to real life things you've heard about before. Okay, so hopefully we can tie a few topics together as we think about solubility. So we've done a lot with equilibrium constants, even back to thermodynamics, where we could find the K, things like that. You've done that. So we could go from thermodynamics and do activity corrections if we wanted to, all of these things to figure out what is the solubility for a given situation. The equilibrium constant is also very useful in relation to what we call the solubility product. So the solubility product, or sometimes also called IAP, ion activity product. Well, that's a slightly separate term. If we say that equilibrium constant is the solubility product, KSP, we can relate that to the IAP. Now, I'm just going to say we'll relate it to it. I think I've got a full slide on this. And we do that to figure out whether or not we're going to dissolve, do nothing, or to precipitate. So we're going to make a relation between these two, the KSP value. If we look at that in relation to the current situation of the water, then we can know what direction we're going to move. We'll say, we'll check the condition of the system.
In terms of direction, do you mean like spontaneous, non-spontaneous?
Yeah, and by direction, I'm referring to whether or not we're going to precipitate or dissolve the. Yeah. Okay, so the ion activity product, IAP. We're frequently going to use this in kind of high concentration systems. And what we're dealing with it is to, like I said, compare how the current situation relates, how it compares to where we have equilibrium. So the ion activity product does not mean we're at equilibrium. The K defines what equilibrium is, and we can compare the ion activity product to the equilibrium value to see whether or not we're going to dissolve or precipitate or whatever. So IAP, this is like the current situation. It's not necessarily equilibrium. Okay. I need to take a moment. I'll be right back. If I had planned my sneeze better, I could have let you watch the video while I was blowing my nose. All right. So, ion activity product. This is if we set K equal to the stuff on the right. The stuff on the right even might be in a condition where it's not equal to K. It's going to move towards K as we move towards equilibrium, but the ion activity product is what's on the right before we've reached equilibrium, if that makes some sense. So normally we say K equals products over to reactants. That is true at equilibrium. We're going to say the ion activity product is equal to, and of course, the reactants, by the way, this just goes to 1. So that's the solid, right? So the ion activity product is simply going to be the products at the current state. I will say it's products over reactants, but that's also going to go to 1, right? So when we talk about ion activity products, that first line up there is showing exactly that. We have the activity of calcium times the activity of sulfate. For that example is the ion activity product. So that means if our IAP is less than the solubility constant, we're not going to have any solid present in solution. So if we stop and think about that, what we're saying is the current situation, if in the current situation this value comes out to a value that's less than K, we're not pushing stuff over towards K. All right? So if we think about this in terms of whether or not we're pushing the reaction to the left or pulling it to the right, if we have a large product over there on the right, maybe product's not the best word, a large multiplication, a large value over there, it pushes things towards the solid. However, if the equilibrium says, well, the spot where we find equilibrium, where the rate at which we're going towards the solid is the same as rate going towards the dissolved products, if that value is larger than what's currently there, it's all dissolving. Okay, so basically we just can't keep up. There might be something precipitating instantaneously, but it's not keeping up. The rate at which we're dissolving is just too fast, so we never have any real solid there. Okay, now if we get an ion activity product equal to the solubility product, the precipitation is ready to occur, or maybe we're just simply balanced. Okay, now if we have a situation where the ion activity product is larger than our K, our solubility product there, then we are definitely going to be precipitating. We can sometimes cause this to happen. If you've done the little experiment by dissolving a bunch of sugar in hot water and then cooling it down and then giving it some seed or like a thread or something to crystallize on, we can then see that happen in action pretty quickly. So got a little video. This is lead iodide as another example for us.
Lead salts are toxic. Do not recreate this experiment. Welcome back everyone for today's experiment. 3.2 grams of lead to acid.
And again, hopefully the creators of these videos, I hope they don't mind. I'm using it for classroom purposes. I think
trihydrate
it's probably good.
And 2.9 grams of potassium iodide are needed. We started off by weighing out the potassium iodide. Potassium iodide is this white salt, which we then dissolved in approximately 50 milliliters of distilled water. On a piece of paper, we weighed out the lead to acetate trihydrate. Lead nitrate could also be used. This lead acetate was made in a test run without using any exotic chemicals, not even hydrogen peroxide or lead-2 oxide. I'm going to repeat this. If you don't want to miss out on this high-yielding preparation of this lead salt, make sure to subscribe to my channel. The lead acetate was dissolved in distilled water. Judging from the cloudiness of the solution, my distilled water likely contained some carbon dioxide. Formed carbonic acid reacts with the lead acetate to form insoluble lead carbonate. A small amount of acetic acid was added to make the solution clear up again. Time for some action. Let's combine both of the solutions. Upon contact, the yellow precipitate immediately falls out. This is lead to iodide. On the top, you can see the reaction that was taking place. Now that we have made this precipitate, it's time to dissolve it again. We place the flour.
So in that moment, we saw that the ion activity product was suddenly very large, right? Larger than the solubility product. So instantly, a whole bunch of precipitation is happening. That's the deal, right? Give it the conditions, precipitation is going to happen. As soon as it mixes with the other solution, it's triggering that precipitation. We get a bunch of solid, in this case, it looks a little like gold, right? But it's the lead iodide.
Flask into heating mantle, which we then turned on. Next time I'll use small amounts of reagents because this was way too much. Some of the lead iodide didn't want to dissolve and sank to the bottom.
So he heated it up to change the solubility constant. We saw that we can calculate how temperature changes the solubility constant. He heated it up, dissolved it all, so that instead of just in that exact spot where the solutions met, it was causing the precipitation. Now it's going to be, as it cools back down, anywhere in solution will just kind of randomly start precipitating. And it looks really cool when he does that.
Even if you can't see it here. 2 hours later, lead iodide finally started to crash out again. We got this effect, which looked like golden rain. Lead to iodide has a poor solubility in water. At 100 degrees Celsius, 1 liter of water approximately dissolves 4 grams of lead to iodide. In comparison to that, 1 liter of water at 20 degrees Celsius just dissolves 0.7 grams. Enjoy the next minute of uninterrupted spectator time.
It's actually a little bit mesmerizing. So this is just slowly precipitating, and he's got it on a time lapse, of course. It's like a little snow globe, right? It's gonna look tasty. Right.
Bottom. I wanted to keep the lead to iodide for my compound collection. To obtain it, we first decanted off most of the solution into my heavy metal waste canister. A vacuum filtration was carried out and the flask was afterwards swirled a few times using distilled water.
So he's just collecting it now.
We were left with this dry, gold-like looking solid. To dry it completely, it was left in a vacuum chamber over anhydrous calcium chloride for a few hours. We were left with 3.5 grams of this fake gold.
Okay, so I think that's what's that?
I said he just had all this stuff on him.
You'd be surprised. There's some great chemistry channels out there that they do some crazy stuff with in their backyard.
What does he mean? He has a collection. What is he doing with it?
Okay, I clearly need to bring in a few more YouTube channels here because there's some good ones out there that are like, where'd you get that? What'd you make that from? Yeah, so, some people, chemistry could be a hobby, right? You thought you were just learning it because it's really fun to learn in school, right? Okay, I think I'll probably leave it off there. We've got a a couple more things to talk about with solubility. It'll relate to redox as well. So we'll see you on Tuesday.